You've heard the name the Milky Way, but this isn't just a river of stars swirling overhead. It's an ancient crossroads of myth and a galactic beast with secrets still untamed. Across 5 great civilizations, people called it the Silver River, the Spine of Night, Akashganga, a bridge connecting lovers, gods, and ancestors. What none could have imagined, lurking at the center of this glowing mystery is a hidden force powerful enough to tear stars apart. For centuries, we could only wonder from Earth. Now, a journey to the center of the Milky Way will take you from those first myths to discoveries that have shattered everything we thought we knew. So what really lies at the heart of our galaxy, and why does it matter for our future? In the southern deserts, under skies untouched by city lights, the sand people gathered around their fires and watched the Milky Way arc overhead. To them, it was more than a mere band of light. The sand called it the spine of the night, a living highway for souls, a guide for hunters, and a memory of creation itself. Their stories reach back thousands of years, carried in the voices of elders in the hush of the Kalahari wind. One story begins with a girl, restless and hungry, waiting for her kin to return from the hunt. Alone by the embers, she grew impatient. In a moment of defiance, she scooped up a handful of glowing ash and flung it skyward. The ashes scattered, taking root in the darkness as a pale, shimmering trail. The Milky Way, the sands say, is that trail of campfire ash, still lighting the way for travelers lost in the night. When the moon hides, its glow becomes the only path home. The tale is not just about the stars, but about longing, generosity, and the power of a single act to change the world. Some say the girl's ash became a bridge for spirits, others that it marked the passage for ancestors moving between worlds. In the sand tongue, every telling weaves in the rhythm of the land, roots roasting in the fire, the hush of the veld, the anticipation of return. The stars themselves are kin, their patterns echoing the movements of animals and the cycles of rain. For the San, stories are not separate from survival. The spine of the night reminds them that every journey is shared. Every campfire connects the living to the departed. In the hush between stories, the Milky Way remains, a silent witness, a memory of a girl's gesture, and a promise that even in the darkest hours, there is always a way home. In the high Andes, shepherds once watched the Milky Way rise as a river in the sky. To the Inca, it was Mayu, the celestial waterway that mirrored the winding Urubamba below. The river's dark patches were not empty. They were alive with shapes: llamas, foxes, partridges, each animal traced in the velvet clouds that drifted across the band. When the rainy season neared, the hampatu, or toad, appeared in the river's darkness, a sign that it was time to plant. The Yakana, the great llama, stretched her long form between the Southern Cross and Scorpio, her eyes bright with the twin fires of Alpha and Beta Centauri. The Incas believed these animals drank from the Sky River, then descended to water the earth, linking the fate of crops and herds to the patterns above. Across the world in India, the Milky Way became Akashganga, the Ganges of the heavens. For Hindus, this was no ordinary river. It was sacred, a cosmic thread binding the earth to the divine. The story tells of the sage Bhagaratha, whose prayers brought the river Ganga from the heavens to purify the world. As the water cascaded from the sky, Shiva caught it in his hair, breaking its fall and sending a stream to earth, while the rest remained in the heavens. Pilgrims still look up and see Akashganga as a bridge between the mortal and the eternal, a path for souls seeking liberation. During festivals, Rangoli patterns at doorways echo the river's arc, inviting prosperity and blessings from the sky. The Greeks saw the Milky Way as a trail of milk spilled by the goddess Hera. The word itself, galaxy, comes from the Greek galaxias, meaning milky circle. According to their myth, the infant Heracles was placed at Hera's breast while she slept. Startled awake, she pushed him away, and her milk sprayed across the heavens. leaving a luminous scar that still circles the night. For the Greeks, this celestial milk was both nourishment and boundary, a sign that even the gods left traces in the world of mortals. Again and again, cultures imagined the Milky Way as a river, a road, a bridge, a luminous path connecting worlds. In these stories, the galaxy is not a distant object, but a living presence, guiding migrations, marking seasons, and carrying souls across the void. The same band of light, mapped by different eyes, became a canvas for longing, loss, and hope. Each myth hints at questions that stories alone could not answer. What lay behind the glow? Was it truly a river or something stranger? A gathering of countless unseen fires? The urge to look closer, to reach beyond the tales, would one day change how we see the galaxy forever. In the heart of Renaissance Europe, a quiet revolution began with a single, unsettling idea. Nicholas Copernicus, a Polish cleric and mathematician, spent his evenings surrounded by charts and ancient texts, questioning the order of the heavens. For centuries, the prevailing wisdom had placed Earth at the center of the cosmos. The sun, planets, and stars, it was believed, orbited around a fixed and motionless world, a view so deeply woven into faith and philosophy that few dared to challenge it. But Copernicus saw patterns that didn't fit. The planets wandered in strange loops across the sky, sometimes moving backward against the stars. The old models, filled with circles upon circles, epicycles stacked to explain every irregularity, grew ever more tangled. In his study at Frombork, Copernicus began to sketch a different cosmos, one that placed the sun, not Earth, at the center. The Earth, he argued, was just another planet, circling the sun along with Mars, Jupiter, and Saturn. The backward paths of the planets, those puzzling retrograde motions, became simple illusions, tricks of perspective as Earth overtook its neighbors in the cosmic race. He worked in secret for decades, wary of the storm that such a claim might unleash. Only in 1543, as his health failed, did Copernicus allow his great work, De Revolutionibus Orbium Coelestium, to be published. The book's pages quietly redrew the map of the universe. In this new order, Earth lost its privileged place. The heavens were not fixed, they were in motion, governed by rules that could be written in numbers and observed by anyone with patience and courage. The sun-centered model did not immediately sweep away the old beliefs. Many dismissed it as a mathematical trick, useful for calculations, but not to be taken literally. Yet the seed had been planted. By stripping Earth of its cosmic centrality, Copernicus opened the door to a new kind of astronomy, one grounded in observation, willing to question tradition, and hungry for evidence. The sky, once read as a tapestry of stories and omens, became a field of inquiry, waiting for new eyes and sharper instruments. The quiet revolution begun by Copernicus would soon demand proof, and the world would never look at the heavens the same way again. Galileo Galilei was born in Pisa in 1564, restless and sharp-eyed in a world that still clung to Aristotle. By the time he reached middle age, a new device had appeared in Europe, a simple tube of glass and brass, imported from the Low Countries and sold as a curiosity. Galileo took one apart, rebuilt it, and pointed it toward the sky. What he saw would upend centuries of authority. In the winter of 1610, he discovered 4 tiny points of light near Jupiter. Night after night, he watched them dance around the planet, vanishing behind it, reappearing on the other side. These were not stars. They were moons, worlds in orbit around another world. For the first time, something in the heavens moved around a center that was not the Earth. With his refractor, Galileo mapped the phases of Venus, saw craters and mountains on the moon, and traced the jagged edge of the Milky Way into a multitude of faint stars. Each observation chipped away at the old order. The universe was no longer a set of perfect spheres circling a stationary Earth. It was a place of roughness, motion, and complexity, open to anyone with patience, a steady hand, and a good lens. The telescope did not just reveal new worlds, it sparked a war over how to know what was true. Galileo's findings angered church authorities and philosophers alike. He was summoned to Rome, forced to recant, and spent his final years under house arrest. But the evidence could not be unseen. The data, written in the language of light and shadow, began to outweigh tradition and doctrine. The sky was not fixed, it was a laboratory. 3 centuries later, that same hunger for proof would play out on a grander stage. In 1920, 2 American astronomers, Harlow Shapley and Heber Curtis, stood before the National Academy of Sciences, each armed with photographs and calculations. The question, were the spiral nebulae, those faint, swirling smudges, part of our Milky Way, or were they distant galaxies of their own? Shapley argued for a vast Milky Way, with everything inside it. Curtis countered that the nebulae were island universes, far beyond our own. Their debate echoed Galileo's defiance, observation against authority, measurement against myth. Neither man could settle the question that night, but the argument itself signaled a new era. Within a decade, Edwin Hubble would use a larger telescope to find Cepheid variables in the Andromeda Nebula, measuring its distance and proving it lay far outside the Milky Way. The universe was bigger than anyone had imagined. The lesson, first glimpsed through Galileo's lens, was clear. The path to the center of the Milky Way and beyond would be mapped not by stories, but by evidence. In the early 1940s, astronomers faced a stubborn mystery. The Milky Way's shape remained hidden behind thick curtains of interstellar dust, blocking visible light and leaving only hints of the galaxy's true form. Optical telescopes, no matter how powerful, could not see through the dark. The answer would come not from glass lenses, but from radio waves, signals that slip past dust as if it isn't there. In Leiden, Jan Oort and his student Hendrik van de Hulst studied the chemistry of space and calculated that neutral hydrogen, the galaxy's most common element, should emit a faint signal at a wavelength of 21 centimeters. Van de Hulst's prediction, published in 1944, seemed almost fanciful at the time. Detecting such a weak signal would require new technology and a different kind of astronomical patience, but the prospect was irresistible. If hydrogen could be mapped, the entire structure of the Milky Way might finally come into focus. The breakthrough arrived in 1951, when Harold Ewan and Edward Purcell at Harvard detected the 21-centimeter line using a makeshift radio dish and surplus radar parts. Within weeks, Dutch teams at Kootwijk confirmed the result. Suddenly, astronomers could track vast clouds of hydrogen all the way across the galaxy, measuring their motion by the shift in radio frequency. For the first time, the spiral arms began to materialize, not as artistic guesses, but as features traced by real data. The sun, it turned out, sits not at the center but near the edge, looking inward at a swirling pattern of arms that wrap around the core. Oort's group, working through long nights and cold winters, pieced together the first rough map of the Milky Way. The spiral structure emerged from the static, revealing the galaxy as a disk more than 100,000 light-years wide, spinning with hidden order beneath the dust. The radio pioneers had opened a new window on the cosmos, trading the limits of sight for the reach of sound. Their work set the stage for a new era of galactic cartography, where each improvement in precision would bring the Milky Way's true architecture into sharper view. The challenge ahead, to move from outlines and shadows to a map drawn with the accuracy of a surveyor's hand. The European Space Agency's Gaia probe set out in 2013 with a single audacious goal: to chart the Milky Way in 3 dimensions, star by star. For centuries, astronomers had worked from the inside, their view clouded by dust and distance, like travelers lost in a forest trying to draw its shape from the ground. Gaia changed the game. Orbiting far from Earth's atmosphere, it swept its twin telescopes across the sky, measuring the positions, motions, and colors of stars with a precision never before possible. Each observation was a pinpoint, Tiny, but together they revealed the galaxy's true architecture. By 2022, Gaia's third data release had cataloged over 2 billion stars. The numbers alone stagger the imagination. Distances measured to within a hair's breadth, across thousands of light years, proper motions charted for stars on the far side of the galaxy, and a map so detailed it could trace the subtle warp of the Milky Way's disk. The Sun, once thought to be near the center, is now known to ride the outskirts, about 27,000 light-years from the core, perched just above the midplane on a gentle wave. The disk itself is not flat but bends and twists, shaped by ancient collisions, and the tug of smaller galaxies still circling our own. For the first time, the spiral arms are no longer artistic guesses. Gaia's data shows them as real structures, patchy, sometimes broken, sometimes branching, but unmistakably present. The local arm where our sun resides stretches farther than earlier maps suggested, winding between the grander Perseus and Sagittarius Carina arms. The disk's warp, once a curiosity, now appears as a rolling distortion, a ripple frozen in starlight, likely stirred by the Sagittarius dwarf galaxy as it plunges through the Milky Way's outskirts. At the galaxy's heart, Gaia revealed an unexpected shape. The bulge is not a simple sphere, but an X-shaped structure, its arms reaching out above and below the plane. This central bar, made of old, red stars, twists around the core and channels gas inward, fueling new starbirth and feeding the supermassive black hole at the center. The scale is immense, over 100,000 light-years from end to end, yet Gaia's map renders it with the fine detail of a surveyor's hand. The data does more than draw boundaries. It exposes motion. Stars swirl in great streams, some racing ahead, others lagging behind, their orbits shaped by gravity and the ghostly presence of dark matter. Young clusters trace the spiral arms like beads on a string, while older stars drift farther afield, their paths revealing the galaxy's restless past. The map is not static. It breathes, shifts, and tells a story of billions of suns caught in a cosmic dance. What Gaia delivered is more than a census. It is a living atlas, one that makes the Milky Way's hidden order visible for the first time. Every star, every arc, every ripple is a clue. The structure that once seemed out of reach now stands before us in sharp relief, a galaxy mapped not by myth or shadow, but by the light of 2 billion distant suns. At the heart of the Milky Way, a puzzle drew astronomers into a decades-long race. The core looked calm, veiled behind clouds of dust and gas, but something massive tugged at the stars packed around the center, a force so strong it sent them whipping through space at breakneck speeds. Two teams, led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute, set out to track these stars. Each group worked for years, peering through the haze with the sharpest instruments on Earth. Their quarry, Sagittarius, a star, a faint radio source hidden behind 26,000 light-years of cosmic clutter. Every orbit they mapped was a clue. The stars, too, a favorite of both teams, traced a tight ellipse around the invisible center. In 2018, S2 swung just 17 light-hours from Sagittarius A star, closer than Neptune is to the Sun, and at that moment it hit a blistering speed of 4,300 kilometers per second. No ordinary object could hold so much mass in so little space. The calculations pointed to a single answer: 4 million times the mass of the Sun, packed into a region smaller than our solar system. The rivalry between Ghez and Genzel's groups drove the science forward. Each published results, double-checking every measurement, pushing for sharper images and more precise orbits. Their competition became a crucible for accuracy. Both teams watched as the stars looped, sped up, and curved in ways only Einstein's equations could predict. The orbits precessed, not as Newton would expect, but as general relativity demanded, a rosette pattern, unmistakable and elegant. The evidence piled up, but astronomers wanted a direct look. In 2017, the Event Horizon Telescope, A network of radio dishes stretching from Hawaii to the South Pole focused on Sagittarius A star. The challenge was immense, imaging something smaller from Earth than a donut on the moon. After years of data wrangling, the result came in 2022. The image showed a glowing ring, 51.8 microarcseconds across, with a shadow at its center, the event horizon itself. The pattern matched simulations of a spinning black hole, not a ball of stars, not a cluster of dark objects, but a single point where gravity reigns supreme. The case was closed. The Milky Way's core is anchored by a supermassive black hole, proven by the dance of stars in the first ever image of its shadow. For their relentless pursuit, both Ghez and Genzel received the Nobel Prize, their rivalry cemented in the history of cosmic detective work. Yet even as the evidence became irrefutable, the center of the galaxy held on to its mysteries, hinting at deeper forces still waiting to be uncovered. Beyond the bright core, the Milky Way dissolves into a faint, ghostly halo. Here, the familiar rules break down. The stars thin out, but the galaxy's mass does not. For decades, astronomers tried to weigh the Milky Way by tracing the orbits of its outermost stars and satellite galaxies. What they found defied expectation. The visible matter, stars, gas, dust, accounts for only a fraction of the galaxy's true heft. The rest, about 85%, is invisible. It neither shines nor absorbs light. This is dark matter, a substance known only by its pull. The evidence first appeared in the way stars move. Far from the center, where gravity should weaken, stars and gas clouds orbit at nearly the same speed as those closer in. The rotation curve stays flat, not falling off as Newton's laws would predict if only visible matter were present. This flatness is a clue to something vast and unseen. To keep these distant objects in orbit, the galaxy must be wrapped in an enormous halo of hidden mass, hundreds of billions of solar masses, stretching well beyond the disk. But the halo is more than a silent container. It is a record of violence. The Milky Way has not grown in peace. Over billions of years, it has swallowed smaller galaxies, leaving behind streams of stars that loop and arc through the halo. These stellar streams, mapped by Gaia and other surveys, are the fossil remains of cosmic cannibalism. Each one traces the path of a lost companion, torn apart by tidal forces and stretched across the sky. The halo is full of such relics, ancient globular clusters, shredded dwarfs, and orphaned stars drifting far from the galactic plane. Some of these satellites still circle the Milky Way, locked in slow-motion battles with gravity. The large and small Magellanic Clouds, visible from the southern hemisphere, are the largest survivors. Others, like the Sagittarius Dwarf, have already been torn apart, their stars now woven into the galaxy's outer reaches. These mergers have left scars not only in the stellar halo, but in the dark matter itself. Simulations show that as a satellite plunges through the halo, it stirs up ripples, waves of dark matter that echo long after the visible galaxy has digested its prey. The halo also holds the oldest stars in the Milky Way, ancient, metal-poor relics from the galaxy's earliest days. They move on eccentric, plunging orbits, unbound by the disk. Their chemistry and motions reveal a history of mergers and accretion, a time when the Milky Way grew not by steady accumulation, but by devouring its neighbors. Each new stream or cluster mapped in the halo adds another chapter to the story. Yet the true nature of dark matter remains elusive. It shapes the galaxy, governs the motion of stars, and determines the fate of satellites, but it cannot be seen or touched. Its presence is betrayed only by gravity, a silent architect sculpting the Milky Way's form and holding its empire together. In the outskirts, where the stars grow thin and the night deepens, the galaxy's invisible mass stretches on, hinting at mysteries still unsolved and a future shaped by forces we have yet to name. Andromeda glides toward the Milky Way with silent purpose, a spiral galaxy as vast as our own and closing the gap at 110 kilometers per second. On a cosmic timescale, it's a slow-motion ballet, two giants drawn together by gravity, each trailing a retinue of stars, yet in satellite galaxies. Every year, the distance shrinks by millions of kilometers, a journey that's been underway since before the first mammals walked on Earth. Astronomers have mapped Andromeda's approach using the faint Doppler shift in its starlight and the precise motions of its stars, measured by Gaia and Hubble. The numbers are unyielding. 4 million light-years once separated us, now less than 2.5. The collision is inevitable but not immediate, a meeting set for 4 billion years from now. Simulations show the encounter in breathtaking detail. As the galaxies draw near, their outer halos of dark matter and stray stars will begin to mingle. Tidal forces will stretch and twist the spiral arms, flinging great arcs of stars into intergalactic space. The first close pass will scatter some stars into long looping orbits, while others are cast adrift, destined to wander the void. Over the next few billion years, the two galaxies will circle one another, their paths tightening with each pass as gravity drains away their orbital energy. Each encounter will trigger bursts of star formation, gas clouds compressed by the violence, igniting new generations of suns. Eventually, the spirals will merge, their shapes dissolving into a single, swollen core. The black holes at their centers, one in the Milky Way, one in Andromeda, will spiral together, radiating gravitational waves before finally coalescing. The end product will not be a spiral, but a new kind of galaxy, a massive elliptical, swollen and smooth, its spiral arms erased by the chaos of collision. Astronomers have given it a name, Milky Way, a single, merged galaxy born from the union of two giants. For any world still orbiting their stars, the night sky will transform. Where once the Milky Way's band arced overhead, now a tangled web of stars will stretch across the heavens. In the final stages, the sun's own orbit will be thrown into uncertainty, perhaps flung farther from the center, perhaps drawn into the thick of the new core. Yet even during this cosmic upheaval, the odds of stars themselves colliding remain vanishingly small. The distances between them are simply too great. The merger will be a dance of gravity and light, not a cosmic demolition. This is the fate written in the motions of the stars, two galaxies, locked on a collision course, shaping a future sky no human will ever see, but one that can be traced in the numbers, in the slow, relentless drift of Andromeda across our telescopes. The Milky Way's story is not finished. Its greatest transformation still lies ahead. The Milky Way is more than a collection of stars and clouds. It is a vast arena where the search for life unfolds on a scale almost too large to imagine. Over the past 3 decades, astronomers have confirmed thousands of exoplanets, planets orbiting stars beyond our sun, spread across every corner of the galaxy that we can probe. These discoveries have rewritten our sense of possibility. Some worlds are scorched giants hugging their stars. Others are frozen orbs drifting in darkness. But a fraction, perhaps a few percent, fall into the narrow band we call the habitable zone, where temperatures could allow liquid water to pool on a rocky surface. Yet the search for life is not just about water or warmth. The galaxy itself shapes the odds. The Milky Way is not uniform. It is layered with risks and opportunities. Near the center, stars crowd together, and the metallicity, the abundance of elements heavier than hydrogen and helium, runs high. Here, planets form easily, but danger lurks. Supernovae erupt with fierce regularity. Gamma-ray bursts and radiation storms sweep through the dense stellar neighborhoods, sterilizing any fragile beginnings. Farther out, the spiral arms thin. The hazards decrease, but so does the supply of planet-building materials. In these outer reaches, stars are poor in metals, and the odds of building rocky worlds drop sharply. Between these extremes lies what astronomers call the galactic habitable zone. It is a shifting ring, roughly 7,000 to 9,000 parsecs from the center, a swath where stars are metal-rich enough for planet formation, but spaced far enough apart to avoid the worst cosmic catastrophes. Our sun sits comfortably within this zone, orbiting at about 8,000 parsecs, in a region where the balance seems just right. Here, the odds of finding Earth-like worlds are highest. The numbers are staggering. Surveys from Kepler, TESS, and Gaia suggest that in the Milky Way alone, there may be billions of planets in the habitable zone of their stars. Some estimates put the count of potentially life-supporting worlds in the tens of millions. But the galaxy is old. Most of its stars, and their planets, are far older than the Sun. If life arose elsewhere, it could have had a head start of billions of years. Life, if it exists, would face a galaxy in motion. Stars drift in and out of spiral arms, crossing regions of higher risk and higher opportunity. The habitable zone itself has changed over time, widening as the galaxy aged and the rate of stellar explosions slowed. Planets born in safe harbors may find themselves, over eons, swept into more perilous neighborhoods, or vice versa. The search for life is a search for context. Each new exoplanet discovered is a reminder that Earth is not alone in its potential. The Milky Way is not just a backdrop, but an active participant, a place that shapes the odds, sets the boundaries, and writes the rules for life's possible emergence. In this galaxy, every world is a test case, every orbit a roll of the cosmic dice. The real question is not whether life could exist, but how many times the galaxy has given it a chance, and whether somewhere it has taken root. In the end, the search for life among the stars is also a search for meaning. It is a reminder that our story is written in stardust, shaped by the accidents of cosmic chemistry and the deep currents of galactic time. The Milky Way holds its answers in silence, scattered across billions of worlds, waiting for us to ask the right questions. The Milky Way spans over 100,000 light-years, with more than 200 billion stars, yet nearly 95% of its mass is invisible dark matter. From ancient stories calling it the Silver River and Akashganga, Ukashganga, to Galileo's telescope in 1610 and the Gaia mission mapping billions of stars today, our understanding has transformed in just a few centuries. Still, key questions remain: the true nature of dark matter, the origins of the galactic halo, and whether life exists elsewhere in our spiral home. Evidence confirms a supermassive black hole, Sagittarius A star, at the core, its presence proven by the orbits of nearby stars in the 2022 Event Horizon Telescope image. Simulations predict the Milky Way will merge with Andromeda in about 4.5 billion years, reshaping the night sky. As of now, astronomers have found thousands of exoplanets, hinting that our galaxy may be rich in habitable worlds. The journey to the center of the Milky Way is ongoing, driven by curiosity and the search for answers written in the stars.